Today we're going to talk about capacitance and dielectrics and or capacitors, okay, in dielectrics. And let's get started. Okay, what is a capacitor? So basically, capacitor is a passive two-terminal electrical component that stores potential energy in an electric field. So capacitor is a passive two-terminal electrical component, meaning when we say terminal, it has a positive terminal and a negative terminal. And these two terminals when connected to a certain circuit, okay, should not be interchanged because interchanging so the terminals could result for a capacitor to burst out or to be what do you call this, busted, okay, because capacitors should be connected according to its polarity, positive and negative. Okay, so what is this capacitor? Basically, two passive two-terminal electrical component that stores potential energy in an electric field. So in other words, capacitor is an electrical component that stores energy in the form of electric field. So how do we form a capacitor? Okay, so a capacitor is actually composed of two conducting plates. Okay, two conducting plates separated with a distance d. So if we're going to draw that, so for example, we have two conducting plates, let's say two charge conducting plates of the same area. Here is a positive conducting plate, and we have another conducting plate here that is negatively charged, and they are actually separated with the distance d. Okay, so because of the charges, we know that there is a presence of electric field between them emanating from positive to negative terminal of the plate. So this electric field enables the capacitor to charge, okay, electric potential energy or energy in the form of electric field. So the requirements must be that for a capacitor, so parts sa capacitor or requirements for capacitor. So number one, we have two charge plates, okay, separated by a distance d. If these two charges touch each other such that there is a physical connection between the positive and the negative plate, that is not a capacitance. Okay, that is not a capacitor, I mean. Okay, two charge plates separated by a distance d. Okay, so and number two, okay, so there must be a dielectric in between. So our lesson is capacitance or capacitors and dielectric. Okay, so there must be a dielectric in between. Now, what is this dielectric material? Dielectric material simply stands for an insulator. Okay, so insulator is a material that is actually what uh, that is actually does not allow the flow of charge easily. That is what we call an insulator. So in between them, in this example, it can be air or what? Free space. Okay? So air is a good dielectric. Okay? But in common capacitors, the dielectrics are typically paper, Teflon, rubber. Okay? Those are dielectrics. So again, for a capacitor, we must have two charge plates, and then that two charge plates must be separated by a distance d. Okay, and in between the two charge plates, there is a dielectric in between. So that's a requirement for a capacitor. Okay, and capacitor is actually look like this in the laboratory. So they come in sizes. Some of the capacitors are really big. Okay, some of the capacitors are really this small. And some of the capacitors are actually a lot more bigger than that. When we talk about capacitor, we are concerned about its ability to store energy. So the capacitor has the ability to store energy in the form of electric field, and it is called the capacitance. Okay, and capacitance is actually its unit is farad, named after the great scientist I don't know, Farad. Okay, but basta that's the unit of the capacitor, farad. So when charged, the conductors carry charges of equal magnitude but opposite sign. So this should be the typical scenario wherein we have a positive charge here and a negative charge here. There is an electric field in between, and they are separated by a distance d. Okay, you can think of this small positive Q and negative Q as charge or conductor, charge conductor. Okay, so capacitors are basically commonly used in variety of electric circuits or electronic circuits. So almost every electronic circuits involves capacitors. So they are very important, or they became a vital part of the electric circuits or electronic circuits because of their various uses. For instance, capacitors are used to tune the frequency of the radio receivers. So have you ever experienced during your childhood, you're actually tuning a manual frequency radio from one station to another station? So the tuning capability of the radio that you have is actually what? Performed by a capacitor. Okay? So that's how capacitors are important even in the old times of communications engineering. So, and another uh, use of capacitor is it acts as a filters in power supply. So, in other words, capacitors are a part of power supply such that if this capacitor is not present in the power supplies in our laboratories or even in our workplace, okay, the AC alternating current would not be purely converted into direct current. Okay, that's one of the uses of the many uses of capacitors. Okay, as I have said a while ago, this is an example of a capacitor wherein we have a two charge plate parallel to each other, positive Q and negative Q separated by a distance d and has an area A, surface area, and of course there's an electric field in between positive Q and negative Q, and of course between them is also a dielectric. Okay, so to formally define, the capacitance of a capacitor is defined as the ratio of the magnitude of the charge and the ratio of the magnitude of the potential difference. I'm so sorry, this should be the magnitude of the charge over the magnitude of the potential difference. Okay? So is in other words, to put it mathematically, to get the capacitance of any capacitor, we can get the capacitance by simply using this formula. C is equals to Q, the magnitude of charge of any charge plate here, divided by the voltage difference or the potential difference between them. Okay? And of course, another formula is that we have epsilon sub 0, wherein epsilon sub 0 is the permittivity of free space, okay, multiplied by the area of the plate, one plate, over the distance between them. So this is the formula for capacitance. So where C is capacitance in farad, again, the unit of capacitance is farad, represented by big letter F. So if you see a 1F, that should be equal to 1 farad, and 1 farad according to this formula is 1 coulomb per volt because of the charge per unit volt. And of course, this epsilon sub 0 is constant. It could never be changed, and it is equal to 8.854 times 10 raised to negative 12 farads per meter. Okay, so we have two formulas. Let's try to write it down. So for capacitance, we have Q over delta V, or it's simply equal to epsilon sub 0 of times A over D. This should be our capacitance. Okay, so again, the other view of the capacitors or two plates is this. If we are going to look at it, so the electric field in the wire applies a force in the electrons in the wire immediately outside this plate. Okay, this force causes the electron to move onto the plate. So, well, of course, what he trying to say in this sentence is that in order for us, of course, to have a charged plate, so it must be connected to a voltage source. Okay, because if that is not connected to a voltage source, then definitely these plates would not be charged. Okay, so once it is charged, again, this is the parallel plate charge, and we have an electric field. Some of the electric field actually what? Diverges outside the plate. And this, the capacitance that this plate or this electric field produces is what we call the fringing of this electric field here produces what we call the what? The fringing capacitance. Fringe capacitance is present. Fringe effect occurs when the electric field extends the area overlap. Okay, because some of the electric fields are actually fringing on the side, so it produces a fringing capacitance. Okay, so that's a fact. And of course, we are also concerned with the electric field inside the charge or inside the plates. So we have to calculate the electric field. In order for us to calculate the electric field inside between the two charge plates, we can use this formula. Okay. So never mind this. This is a simplified formula where electric field is equals to the magnitude of charge over the epsilon sub 0, which is the permittivity of free space, over multiplied by A. So let me just write this again. So what is this again? Electric field. This is the electric field produced by the capacitor. So we have the formula Q over epsilon sub times A. Okay? So let's try. Let's try to solve the size of a 1 farad capacitor. Well, in fact, typical values of capacitors are usually ranges from microfarads, nanofarads, or even picofarads. So let's try to calculate what is the size of a 1 farad capacitor. So in this question, it says a parallel plate capacitor has a capacitance of 1 farad. If the plates are 1 millimeter apart, what is the area of the plates? So, in this given, okay, we can actually calculate the size of the plate. So, number 1, we are given a capacitance of 1 farad, and we have a separation distance between the plates of 1 millimeter. Okay, are we correct? Okay. So, the question is, what is the size of the plate? Well, of course, okay, we are pertaining to area. So again, our formula a while ago is epsilon sub 0 times A over D. So if we get A, we have to use the formula A CD. Okay, so we have C times D over epsilon sub 0. So this distance, we must convert it into meters, always. Okay? So, A is now equal to capacitance 1 farad multiplied by a distance of 1 millimeter, that is 0.001 meters. Okay? Over epsilon sub 0, which is 8.854 times 10 raised to negative 12. By the way, the unit of this is farads per meter. Okay? If we calculate the area, the resulting area would be this. 1.1 times 10 raised to 8 meters square. 1.1 times 10 raised to 8 square meter or square meter. Okay? That is a really huge conductor. Imagine a conductor plate having a 1.1 times 10 raised to 8 square meter or meter square of area. Okay, that's a very large plate. So the 1 farad of capacitor is really big. Even in our classrooms, it could not be fit in there because this area is very large. Okay, so that engineers are going to design a capacitor that has a minimum separation of distance. Okay, and that would produce a capacitance that is actually really small. Okay, so imagine if you have a gadget and inside your electronic gadget you have a capacitor. Okay, that has an area of this. Well, of course, that is not practical. You cannot actually insert this inside your mobile phones because it's actually really large. Okay? So number 2, the plates of a parallel capacitor in vacuum, meaning they are separated, the two plates are separated in the vacuum, okay? 5 millimeters apart and 2.0 square meter area. A potential difference of 10,000 volts is applied across the capacitor. Compute A, the capacitance. So first, let's try to identify the given. So we have a distance of 50 50, 5 millimeters. Okay, so sorry, 5 millimeters. Then we have an area of 2.0 meters square. And we have a potential difference of 10,000 volts. The problem is actually asking what is the capacitance. So for letter A, capacitance is actually epsilon sub 0 again, multiplied by A over D. And our epsilon sub 0 is 8.854. For Casio calculator, that is shift constant 32. Okay, it's a constant stored in your calculator. Multiplied by A, that is 2, over the distance of separation, 5 millimeters, converting that into meters, 0.005 meters. Okay, square. Still meter, because the distance of separation is meter. Never mind the units. So if we're going to calculate that, it should give us the answer of 0.00354 microfarads, or this is equivalent to 3.54 what? Nanofarads. Okay? So imagine this is a very small amount of capacitance. 3.54 nanofarads. And these are the typical values of capacitances of our capacitors. Okay? For letter B, the charge on each plate. So what is the charge on each plate? We have the formula C, okay, is equal to the magnitude of charge over the potential difference. Okay? So we have a capacitor of 3.54 nanofarads. If we're going to get this in terms of charge, that is equivalent to Q is equals to C times delta V. So that we have 3.54 nanofarads multiplied by the potential difference, which is 10,000 volts. So our answer should be what? 35.4 microcoulomb. Remember that this is charge. Okay, what is this microcoulomb? That is the charge on each plate. Okay, the charge on each plate. Letter C, again, the problem is the magnitude of the electric field inside the two plates. So we have the formula E. We have the formula E is equals to Q, if I'm not mistaken, over epsilon sub 0 A. So that is our formula a while ago. What we did. Okay, this is the formula. Let me see. Q over epsilon sub A. So if we're going to get the electric field, the magnitude of the electric field, that should be equal to 35.4 microcoulomb over epsilon sub 0 multiplied by the area, that is 2 meters squared. So if we're going to calculate that, we should get a value of an electric field 2 times 10 raised to 6 Newton per coulomb. This is a large electric field. Okay? So that is our answer. So let's try to recall some circuit symbols, or what we call schematic symbols for some circuit of elements. So these symbols, circuit symbols, or what we call the schematic symbols, are actually used as a standardized symbols in our electronic circuits or electrical circuits for us to easily understand the symbol, rather than you're going to draw the whole element. Okay? For example, we have here the capacitor symbol. The capacitor symbol is represented by these two parallel conducting plates. Okay? And connected to a wire. This is simply a wire. So this is a capacitor symbol. Okay? And we have a battery symbol wherein we have two parallel lines, vertical lines, wherein one is actually longer and thinner than the other. Okay, the one that is longer is the positive side, and the shorter one is the negative side. So this is the battery symbol, and of course the switch symbol, wherein we have here the switch symbol. If the switch is open, it would look like this, and when the switch is closed, it would look like this. Well, of course, the switch performs a control of the current, or controls the current that is flowing in the circuit. So the purpose of switch is again to control the current in the circuit. Okay, so it can either open the circuit, which means there is no current, okay, and it can either close the circuit, which means that there will be current in the circuit. So circuit symbols for capacitors, batteries, and switches. The closed switch carry current, whereas the open cannot carry current. Okay, so here are the typical symbols. So let's try now to actually simplify capacitors into a single capacitor. So let us take note that we can connect capacitors in either what we call the parallel or the series. Okay, so for parallel combination of capacitors, here is the scenario. So we have a voltage source here, which is the battery. We have capacitor 1 here connected in parallel with capacitor 2. So how do you know if these two elements are connected in parallel? Because there is a confusion on that. Okay, you will know if the connection of the two capacitors is in parallel if we have a node here. Okay, so this is called a junction or node here. So in other words, if I'm going to draw it here, for example, okay, that node is equivalent to this, okay, to this tube. Okay, this is a node. So what I'm trying to say is that this node is actually this side. Okay, the intersection of the three wires here. You can think of this as a tube. So when water enters here, some of the water enters here and some of the water enters here. So one cannot simply say that all of the water will actually go here. No, that's not true. Or in other words, all of the water will go here. No, that's not true. In circuits, it should divide. Okay? So in this case, circuits, not water, but the current or the charge. Okay? So that we have the relationship of charges and voltages in the capacitors. So, again, the node is actually the connection where or a point where the connection or a point where three or more what circuit elements are are connected. Okay, so as in this case, we know that these two capacitors are connected in parallel. Okay? And other word for us or other techniques in order for us to determine if the connection of the two capacitors are connected in parallel is that if they don't have the same charge. Okay? In terms of capacitor. In terms of resistors, if they don't have the same current. Okay? So, just like what I've said a while ago, this parallel combination of capacitors can be converted on what we call a schematic symbol for easier understanding. Okay? So this is converted to this sign, this sign, and this capacitor into this circuit symbol. Now, we can actually what? Simplify capacitors connected in parallel, for example, these two capacitors, into a single capacitor. Okay? And that capacitor is what we call the equivalent capacitance. Okay? So for parallel combination of capacitors, okay? For parallel combination of capacitors, there are three things that we need to understand. Okay? Number one, okay, to get the C equivalent of any capacitors connected in parallel, we simply add the value of their capacitances. Okay? Well, of course, in our example, there are two capacitors. Well, if there are three capacitors connected in parallel, simply we have to add, let's call that C sub n. Okay? So, for number 2, pretty easy, right? So, number 2, we must remember that the voltage drop, the total voltage drop, is equal to the voltage drop across capacitor 1 and equal also to the voltage drop across capacitor 2. So, in other words, if we have two capacitors connected in parallel, they have the same voltage. Okay? So, in other words, this voltage source, which is V sub T, okay, has a voltage sum V. Okay? And the voltage drop across capacitor 2 is equal to this voltage because it is in terms of in parallel with C sub 2 or with the voltage source. And of course, if C sub 2 is also in parallel with C sub 1. So whatever the voltage here in C sub 2 is the same as the voltage here in C sub 1 because they are connected in parallel. Okay? So, number 3, we have to remember that the total charge in the circuit, okay, when I say total charge, is actually equal to the charge through capacitor 1 plus the charge through capacitor 2. In other words, these two capacitors are what? They don't have the same charge because they are connected in parallel. And in order for us to get the total charge in this circuit, we must add the charge here at capacitor 2 and charge here at capacitor 1. The only time that they will become equal in charge if they are the same in capacitance. Okay, but if they don't have the same capacitance, definitely they don't have the same charge. Okay, so these are the important things about the parallel combination of our capacitors. Okay, so you must remember that. Okay, so the total charge on a capacitor connected in parallel is the sum of the charges of the individual capacitor. That's what I'm trying to say a while ago. Q total, this is represented by this. And we have the equivalent parallel capacitance combination of capacitor is simply the algebraic sum of the individual capacitances. So if we're going to get the total capacitance or the equivalent capacitance, simply use this formula. And again, there is a great concept, okay, in this combination of capacitors in parallel. If we're going to get the total capacitance of capacitors connected in parallel, our result must be greater than any of the individual capacitances. Okay? So for example, we want to get the, let's say, this is our voltage source. This is our capacitor 1. This is our capacitor 2. So they are both, let's say this is 2 microfarads. Let's say this is 3 microfarads. And I want to get the total equivalent capacitance. So we simply what? See equivalent since they are connected in parallel. 2 microfarads plus 3 microfarads is equal to 5 microfarads. So it is very obvious here in concept that the C equivalent or the total capacitance value that we are going to get if we have capacitors connected in parallel should be greater than any of the individual capacitances. Okay, that's the concept. That's what this number 2 here is trying to say. Okay? And of course, the potential difference across the capacitors connected in parallel are all equal to our source or to the voltage source. Okay, that's what I'm trying to tell a while ago. Okay, if we have parallel combination of capacitors, well, of course, we have also series combination of capacitors. And of course, if we have two series combination of capacitors, how do we know if the two capacitors or two elements are connected in series? If they have the same charge or if the same current flows through them. Okay, in this case, these two are connected not in any junction, but simply in series. Okay, so we can say that these are the series combination of capacitors. And of course, what are we going to remember in series? Okay, pretty easy. If we want to get the total capacitance or the equivalent capacitance of any circuit, we should not be using this formula. I discourage you to use this formula, but rather, we should use this formula. So if, let's say, if two capacitors are connected in series, so we can use this formula, C sub 1 raised to negative 1 plus C sub 2 raised to negative 2, and altogether their sum is raised to negative 1. Okay? So that's the easier part here. So this formula applies to any, okay, to any capacitors connected in series. Even it's 3, 4, 5 capacitors, you can always use this formula. Or if we have two capacitors connected in series, we can simply use the product over sum formula. But this formula is only valid for two capacitors connected in series. Okay? So it is much advisable to use this formula. Okay, number 2, in terms of voltages of capacitors connected in series, the total voltage is actually equivalent to what? The voltage drop at capacitor 1 plus the voltage drop at capacitor 2. What does this mean? If we have capacitors connected in series, meaning they don't have the same voltage drop, except if they have the same capacitance again. Okay, but as long as they don't have the same capacitance, the voltage drop across any two series capacitors are not the same because they are connected in series. For number 3, we have the charge, and the total charge is simply what? Equal to the charge through capacitor 1, and equal to the charge at capacitor 2. I see the 2 and 3 here for series and parallel are interchanged. Okay? So this is the important concept we have to know, or we have to identify in order for us to solve circuits involving the charge, the voltage drop, and capacitances of capacitors. So here again, this is what I'm trying to tell you a while ago. The great concept of combining capacitors in series is that if we get the total capacitance of a capacitors connected in series, we should get an equivalent capacitance that is what? Less than any of the individual capacitance. Okay? So if we're going to try that, okay? If we're going to try that, for example, we have here a battery, we have capacitor 1, this is capacitor 2, and let's say these two both are 6 microfarads. Okay? 6 microfarads. If we wish to get the total capacitance or the C equivalent of that, that should be what? 6 microfarads raised to negative 1. 6 microfarads raised to negative 1 plus 6 microfarads raised to negative 1, and they are raised to negative 1. Simply, we could get C equivalent of 3 microfarads. And the total capacitance now is less than any of the individual capacitance. So in short, if we want to get a total capacitance, if we want to lessen the capacitance of a circuit, connect the resistor connect the capacitors in series. If we want to lessen the capacitance of the capacitor, the circuit, the total capacitance of the circuit. While if we want to increase the capacitance of the circuit, the total capacitance of the circuit, connect the capacitors in parallel. Okay, I hope you are getting what I'm trying to say here. These are very important concepts. And of course, okay, so for example, this, or maybe this one first. Okay, for example, so 9 microfarads are connected in parallel. What is the total capacitance? So we have, let's say, for number 2 first, we have 3 microfarads connected in parallel. So these 3 microfarads are connected all in parallel. Okay, they are all connected in parallel. This is C sub 1, C sub 2, C sub 3. Okay, what is the total capacitance? So again, if we want to get the total capacitance of capacitors connected in parallel, what should we do? We simply what? Add their capacitances. So in this case, you have 9 microfarads. I'm so sorry. The given is 9 microfarads. So 9 microfarads, we have 9 microfarads plus 9 microfarads plus 9 microfarads. Simply that is equivalent to 27 microfarads. Okay, that is for number 2. For number 3, the capacitors of a certain electrical circuit is composed of 5 capacitors in series. So we have 5 capacitors in series, connected in series. So we have what? So we have to draw 1, 2, 3, 4, 5 capacitors connected in series. And this is 1 micro, this is 2 microfarad, 3 microfarad, 4 microfarad, and we have finally 5 microfarad. So the problem is asking us what will be the total capacitance of this circuit. Well, we all know if we are going to connect capacitors in series, we must get an equivalent capacitance that is actually what? less than any of the individual capacitance here. Okay? Or maybe less than 1 for sure. So you will know if your answer is correct if your answer is less than 1. So let's try. So for capacitance, total capacitance connected in series, since we have 5 capacitors, so we have C sub 1 raised to negative 1 plus, yes, we have this formula. Okay? So substitute. So we have 1 microfarads raised to negative 1 plus 2 microfarads raised to negative 1 plus 3 microfarads raised to negative 1 plus 4 microfarads raised to negative 1 plus 5 microfarads raised to negative 1, and they are altogether raised to negative 1. So what would be the answer? If you wish to calculate this in your calculator, well, definitely that should be 0.438. 0.438. I think this is microfarads. Okay? I think this is microfarads. I forgot to write microfarads in there. Here. This is in terms of microfarads. Okay? Okay. For number 4, what will be the potential across the capacitor that has a magnitude of charge 2.1 nanocoulomb and the capacitance 1 nanofarad? The potential across the capacitor. So, if you want the potential, again, the formula is Q over V or delta V. So, if you want the potential here, we have Q over C. Okay? So, what is Q? We have 2.1 nanocoulomb over 1 nanofarad of capacitance. So, simply, this 2 nano will cancel. 2.1 divided by 1, simply 2.1 volts. Okay? Now, let's go back to the first example. So in this problem, we are asked to find the equivalent capacitance between terminals A and B, okay, for the combination of the capacitors shown in the figure. All capacitances are in microfarads. So let me just copy that one for you, okay? So we have here number 5. We have terminals A. We have terminals A and B here. Okay, so that we have 4 microfarads here, and we have 1 and 3 microfarads. 1 and we have 3 microfarads here. And we have another one here, parallel. And here, we have a series capacitance here, capacitor. So what would be the total capacitance between the terminals A and B? So I have 4, 1, 3. 4, this is 1, this is 3. Okay? 6 to 8. Let's say this is 6 to this is 8. Okay? There is no difference if I'm going to draw it like this and this. These are interchanged. Okay? So there's no difference. Okay? So we have this. So all of these capacitances are in terms of what? These are in terms of microfarads. So first thing to do, okay, what will be the total capacitance measured by your voltmeter or by your multimeter? I mean, if you're going to put the positive sign here or the positive probe and the negative probe here, what would be the measured total capacitance? Well, we all know that we can simplify these capacitors into a single capacitance or a single capacitor. So what would be that capacitance? Okay, so let's try to solve the total capacitance. Okay, first we can get the combination of these two in parallel. So let's call that C sub A, and that C sub A they are connected in parallel. So if that is connected in parallel, we simply add them, and that is equivalent to 4 microfarads. And these two also, we can get the combination. So again, that is what? In parallel, 6 microfarads plus 2 microfarads. So we will add them. Okay, so the next thing to do is to draw again the circuit. So we have terminals A here, and we have 4 micro here. And of course, these two capacitor became a single capacitor. That we labeled as C sub A. And we have now another one. These two capacitors is simplified as a single capacitor. So that should now become C sub B. Okay, so we have here C sub B. So this should now be C sub B, and this is still 8 micro, and this is 4 micro. What's the value of C sub A? That is 4 microfarads. This is 4 microfarads. This is 8 microfarads, and this is also simply 8 microfarads. So what we can do is again combine these two. What is the connection between these two? That is in terms of series. Let's call that the combination of C sub C. And that should be equal to what? Since they are connected to series, we have to use the inverse formula. And if you get that, the value of this should be 2 microfarads. And we can also get the what? The combination of this. Let's call that C sub D. You can label it as any thing you want, but for the sake of consistency, I'm labeling it C sub A, C sub B, C sub C, and C sub D. So these are connected in series. 8 microfarads raised to negative 1 plus 8 microfarads raised to negative 1 all over raised to negative 1. That should be 4 microfarads. So that if we're going to redraw again the circuit here, okay, if we're going to redraw again the circuit here, so we have this circuit. These two become now 1. So that is the equivalent. And these two also become 1. And this is, we know that this is C sub T. And this is now C sub C, which is equal to 2 microfarads. And this is 4 microfarads. And we have the terminals A and B. And what's the connection of C sub C and C sub D? They are connected in parallel. Why? Because they have a node here. Okay? These have a node here. Okay, so what will happen? Would you agree with me that the combination of these two capacitors or capacitors is the total capacitance? Yes. So that's the total capacitance. So they are connected in parallel. So simply we add the capacitance of them. So C sub T should now be equal to, what is C sub C? 2 micro plus 4 microfarads. That is equivalent to 6 microfarads. And that is our total capacitance. Okay? So for now, that would be our discussion. Thank you so much for listening. I hope you enjoyed the lessons about capacitors. And in the next video, we'll be continuing the capacitors or the lesson of capacitors part 2. Okay, thank you so much for listening, and God bless you.